Hopefully you did good.
What's 3 factorial?
3 times 2 times
6.
Okay. And how do you get that?
3 times
3
2
3
times
times
1.
2 times 1.
Okay. Nice. 5 factorial.
Is that possible?
Yeah.
So it's 3
Huge.
120?
What?
120?
Usually factorials decrease, right?
I thought they said 5. I didn't even look at the screen.
Pi. Pi.
What would be the step down from 5?
Would it be continuous? And you do an interval?
Yeah, pretty much. You can't take the 5 out of figuring out, but okay. Factors are pretty interesting, right? Because we can definitely define them for integers. When it comes to non-integer real numbers, it becomes a little bit murky because it's always the integer times the integer before that times the integer before that all the way to 1. But then if there's not an integer, then how do you know what the integer before is? Suppose you don't have a calculator, and I ask you to give me pi factorial. It's a test, it's worth 20% of your grade. You need to give me pi factorial without a calculator.
Well, even the calculators have errors.
Yeah,
We
same.
can't really use it.
Good, so I want you to give me pi factorial. How would you go about solving that? You know, maybe not the exact number. Maybe I say, give me pi factorial. Whoever gets the closest answer gets 100. Everybody else gets 0. How can you try to approximate that
I think
number?
I would assume pi is like 3.14 and then put 3.14 times 3 times 2 times 1. That's what they would do.
That's what you would do. I think that wouldn't really necessarily be a factorial, right? But okay, you're thinking of somehow messing with other integers, right? That's good. And any other ideas?
Right, so could you set it up pi factorial, then pi minus 1 factorial, pi minus 2?
That's another way, right? You can say pi factorial, pi minus 1 factorial. That's another way. But then you still have the question, what is pi minus 1 factorial? I like this question, not because it leads into today's topic, but also because the approach to solving it is something that I've had to do in the real world. And I think it's good for us to kind of try it out ourselves. So how would you solve something like that? Again, you know what a factorial is. You know how they work with integers. How can you maybe find a value or a possible value for a number in between the integers? You have pencils, pens, coloring markers, papers, maybe even scissors, I don't know, rulers. You have all the handcrafty tools at your disposal. What would you do? Any ideas, online students? The in-person students are all thinking. I can see their little thinking faces. Maybe not even factorial. Let's not think of factorial. Oh, I'm very faint. I may have to speak louder. The question is, what's pi factorial? This Kennesaw mask is worse than my other masks. The question is, what's pi factorial? Or how do we find it? Is there a method? Maybe something to approximate it. I don't need an exact number. I just want your closest estimate.
So then could you just say greater than 6?
You know it's greater than 6, good. And smaller than,
The next one.
which is? Okay, 4 factorial, 24, good. Okay, somewhere between 6 and 24, all except what you said, right?
Yeah.
Pi minus 1, good, okay. We're getting there, okay. We're getting close. I like what you did, what you just said, greater than 6, and Milton said smaller than 24. Renee gives us a clue, right? Maybe there's a way we can interpolate. So, how do we interpolate? Don't talk about math, just talk about visually, how do we interpolate? What's the visual idea behind interpolation? Christian gives us another idea, 3 factorial times something like that. Okay, I wouldn't do that, but how do you think we interpolate? Bounce from one side to the other until you get close enough. That's good. That's actually iteration, not interpolation, but still pretty good. I'll give you a hint. And this is something that I do not just for my academic stuff, but whenever I need to figure something out. And I kind of know things that are before, after what I need, but I just don't know the exact thing. For example, let's say solving an equation that doesn't have an analytical solution. One way I can go about it is by plotting values that I do know. Because you know this equation, you know what factorials are, right? You just don't know what they are in between the integers. But maybe if we plot them, we can find some relationship. In the chat, a student says interpolation is determining a value between two known values based on a trend between the two known ones. Wow, that's beautiful. So let's do that. What's 0 factorial? What's 0 factorial? 1, good. What's 1 factorial? 1, good. What's 2 factorial? 2, good. What's 3 factorial? 6. Okay, what to say. What's 4 factorial? 24. 24, some number up here, good. We could say, okay, maybe our factorials will look something like this. And now the question would be, is there an equation that kind of gives me something similar to that curve? Now that 0 and 1 is tricky, because 0 factorial is actually just defined, it's kind of forced. It's 0 factorial has to be 1 so that the factorials work for all the other numbers. So maybe let's ignore that 0 factorial, right? And thank you, Jaden, for the help here. But maybe between 1, 2, 3, we can find a function that helps us at least approximate those numbers. In other words, we can maybe draw a little line and find a function for that line, even though it's not exactly the same number, maybe something that's very, very close to that number. And that function already exists. The function is actually called the Stirling formula. This is a nice, really, really nice little formula that helps us approximate factorials for several integers. Now the Stirling formula tells us that n factorial is approximately equal, approximate, not equal, just approximate, to the square root of 2 pi n times n over e elevated to the power of n. You write this equation down for smaller numbers, you'll get a very close estimate, but as your n increases, you get closer and closer to the actual value. And in fact, if you were to plot the ratio between the factorial you get from Stirling's formula for your integers and the factorial you get by hand calculating, 3 times 2 times 1, if you plot that at infinity, they are pretty much the same. So it's a really, really nice approximation that actually converges with the real definition of a factorial. Now, my whole point of this is obviously to introduce a little bit of the content here, but I do want you to get get this idea of using graphical methods. I know a lot of students hate geometry. I don't know why. I like it much more than algebra. But visual, visual tools are very powerful tools. Even though they're not going to get us exact numbers, they're still going to get us close enough to actually be able to draw conclusions, right? So what I'm asking here is, I don't want an exact equation that gives me every single factorial down to the top because that equation doesn't exist. But at least by interpolating, maybe you can find the value for pi factorial which is somewhere in between 3, which is 6, and 4, which is 24. You can try a Stirling formula, but Stirling formula really only approximates integers correctly. But there is a formula that approximates for non-integer real numbers. I think you had already given us a hint of that formula, right? What was the function that we had to do? Integrate, right? Yeah, that's correct. You can tell that we can express this as a sort of series, and if we sum up an infinite number of elements, eventually we're going to end up with an integral. Now that formula, which is the first topic of this class, is called the gamma function. The gamma function is going to be used throughout the rest of this course for defining some probability distributions, but let me just explain what that function is. The gamma function is a function in Greek letter, capital gamma, and we say that, or we define it as gamma of r is a function defined by the integral from 0 to infinity of x to the power of r minus 1 times e to the power of negative x integrated over dx. That's the gamma function. Sometimes other statistics books, mainly non-engineering statistics books, will write this formula a little bit differently by replacing this with, well, x times r minus 1, x to the power of r minus 1 is just x to the r over x, right? So they just write it down a little bit differently. They just say x to the power of r times e to the power of negative r, or negative x, times dx over x, which is the same thing, right? X to the power of r divided by x is x to the power of r minus 1, so it's the same thing. So that is the gamma or gamma function, depending on how you want to pronounce it. And now the question is, well, how does this relate to factorials? Well, you'll find, and you can try this out yourself by plugging in numbers, but you'll find that gamma or gamma of r plus 1 is actually going to be equal to r times, oops, I wrote f, times gamma of r. And how does this tell me that this is related to a factorial? Well, think of it this way, right? Gamma of r plus 1 is equal to r times gamma of r. What function has those properties? Well, the factorial function has those properties, right? So what this tells me, right, what this implies, actually, wrong sign. What this implies is that gamma of r is equal to r minus 1 factorial, or gamma of r plus 1 is equal to r factorial. Gamma of pi plus 1 is equal to pi factorial. And that is the gamma function. Really beautiful function. Allows us to approximate factorials for non-integer but still real numbers, etc. And we can find that some of those values, some of those numbers are actually really easy to remember. For example, if we take gamma of 1/2, gamma of 0.5, essentially what this is telling me is 1/2 minus 1 factorial. So it's negative 0.5 factorial. So if somebody ever asks you what is negative 0.5 factorial, all they have to do is say negative 0.5, add 1 to it, and apply to the gamma function. You plug in 1/2 here, and you're going to get an answer of square root of pi. Really, really nice answer. Square root of pi. So what does this tell me? Well, negative 0.5 factorial is actually square root of pi. We can continue with this. For example, we can try with gamma 3/2. You already know that 3/2 is the same as 1/2 plus 1. And this is the same as 1/2 factorial. And following this property, this is the same 1/2 gamma of 1/2, which is just square root of pi over 2. So that is 1/2 factorial, or just gamma of 3/2. You can continue on 5 halves, 7 halves, etc., 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 and that will give you your factorials, and you'll see that they are pretty much functions of pi. Really, really nice. That is how we determine factorials. Now, of course, this isn't really a math class. I mean, statistics is a math class. This isn't a math class per se, in that we really want to relate this to statistics. So let's figure out how we can relate all this function to statistics. Make sure you take some notes. Perhaps the gamma function is something that you're going to want to write down, maybe in a sheet of paper, maybe in an index card, and keep it with you, because you're going to have to turn back to it on some occasions. Like we're going to be defining some distributions and say, oh yeah, and gamma of whatever, gamma of r, gamma of x, gamma of x, and you'll want to go back to that function in order to calculate those values. So let's try to relate this a little bit to our probability distributions. Does anybody remember what an exponential distribution described? I don't need the formula itself, just what was it? Like, what does it describe? And it was related to a Poisson process, if I remember correctly. When I say describes, I mean, what would you apply the exponential distribution to? Like what type of scenario? What are we looking for? Successive events in the chat. No memory, yeah, that's correct. And that's along the right lines, right? The exponential distribution would give me, right, the length of an interval, right, until the first event occurs in a Poisson process. Now, the exponential distribution, remember, had zero memory, lack of memory property, and all that stuff. We could actually generalize the exponential distribution a little bit, because the exponential distribution, the output of that variable was the time until the next successive event, right? So if you start measuring, we did an example of particle technique. So if you're measuring a particle, the variable for the exponential distribution, so the exponential variable will tell me the time I would reach or detect my next particle. If you're just flipping your coins and you want to end up your heads, the variable will tell me, and I guess it's continuous, let's just say time, the time until I actually land at a success. Now we can actually generalize this just a little bit. Instead of saying we want the time or length or interval until the first event, we can say we want the time or length or interval until any number of events. Let's call them R events. So instead of one event, we just replace that one with any of the number ones. R, 3, 4, 5, 6, 7. That type of variable, that type of random variable, is called an Erlang variable, and it will follow an Erlang distribution. So the Erlang distribution is going to tell us, or it's going to give us, the length, time, interval, you can call it whatever you want, until R events. Before, when we were talking about exponential distributions, it was until one event, but now it's until R events in a Poisson process. It was named after Abner Erlang, who was a Danish mathematician, statistician, and engineer. I really like talking about people who lived years ago, because they're usually never one thing. It's like, yeah, I was this and this and this. Talk about Pascal, it's like really recognized theologian, but also mathematician, but also physicist and engineer. I like all that. But anyway, the Erlang distribution is going to have a probability density function of lambda to the power of r. Remember that lambda was the average number of successes in an interval in a Poisson process, x to the power of r minus 1, and e to the power of negative lambda x, divided by r minus 1 factorial. Now, of course, if the Erlang distribution is a generalization of the exponential distribution, where instead of one event we have R events, it should follow that if we plug 1 into our R here, we should end up with the same exponential distribution function. So you can try it out. We should get the exponential distribution if we plug 1 into R. There are some limits here. For example, x has to be greater than 0. Remember, this is an interval length or time interval. There's no such negative length or negative time, at least for the purposes of this class. But then R has to be an integer as well, because we want successive events, right? We don't want, we want successes. A successor failure, there's no such thing as 1.5 successes, for example. That is the Airline distribution. And even though we do want integers for our number of successes, sometimes, right, we want to find some values in between. And for some values in between, well, we can just write down any real number, any non-integer real number here, and that's fine. But here, we get a problem. And that's, of course, where the gamma function comes in. Now, if we were to generalize the Airline distribution to allow for any R positive value, real value, instead of just an integer, then we say that that random variable follows a gamma or gamma distribution. The gamma distribution, it's generalized, right? We bring in our gamma function in order to generalize this so that our probability density function becomes, well, the numerator is the same, lambda to the power of r, x to the power of r minus 1, e to the power of negative lambda x. But then in the denominator, because we had r minus 1 factorial, we can replace that with my gamma function for r. And this is the probability density function of a gamma distribution. Of course, we need to know the measures of this gamma distribution. And it will follow a mean of r over lambda and a variance of r over lambda squared. Same applies to the Airline distribution, since technically they're the same, except that one is only integers and one is everything. Well, every positive real number. That's gamma distribution. We are going to talk about gamma distribution in a future module, and we're going to go a little bit deeper into it. But since we are in the process of introducing several distributions, and since we will need the gamma function even before we start dealing directly with gamma distribution, I thought it was better to just throw that out there. You can put it in your little table of distributions so you can have it there. A special case of the gamma distribution is and there's 1,000 ways to pronounce this. You can choose whichever one you prefer. So how do you pronounce this?
Chi squared.
You say chi? Okay. You say chi squared? Okay. What would you say? Chi? What would you say?
Chi.
You? Oh, chi. Okay.
Chi.
Okay. Chi. Okay.
I'll say chi.
All right. Good. So this is supposed to represent the Greek letter, right? He. So I would say if you're Greek, you probably call it a chi-square distribution. If you're a fraternity Greek, then you would call it a chi-square distribution. And then if you're everything else, then chi or chi-square distribution. Yeah. There's, I'm not a language purist. Like, if I can't pronounce something, I'll just give it my shot. But because I speak Greek, then I prefer definitely to just call it a chi-square distribution, just because it's easier. If you don't speak Greek, then just call it a chi-square distribution. Doesn't matter. Just don't call it a chi-square distribution. That's like makes you sound like a frat person. Lose a little bit of respect for you there. No offense. Anyway, this distribution is a generalization, or not generalization, sorry, a special case of the gamma distribution. And for this distribution, lambda is going to be equal to 1/2, and r is going to be any number in succession from 1/2 to 1 to 1 plus 1/2 to 2, and so on. So r can be any half step real number, and lambda has to be 1/2. You just plug in whatever values into the gamma distribution, and we'll say we said that follows a chi squared, chi squared, chi squared distribution. And again, we are definitely going to cover this in more detail when we talk about these types of special distributions. What I do want you to pick up from here is the gamma function. That's the important thing here. If you want to try some examples on your own, because you will be able to solve 1 or 2 examples in the homework, then you can try examples 419 and 420 from your book. I think those are pretty straightforward. They give you what it is you need, lambda, r, and then you just plug it into your gamma distribution and then find the answer. The title of this week's, I guess today's material was more distributions, because really I just wanted to go over an introduction to all the distributions. Looking back, I don't think that was the best way to organize the class, but I mean, we're already here. So maybe for the next time I teach it, I'll move things around. But you may have realized that every single distribution we've talked about, how many random variables did they have? Right now, how many random variables are in each of these distributions? R is fixed, lambda is fixed, right? They're just part of the system. How many variables do I have? Yeah, just one, right? And what's that variable? X. Yeah. So every single distribution we've talked about so far, and thank you, Renee, in the chat as well. Every single distribution has had only one random variable. But we've already talked about several examples where there's more than one random variable. In fact, even for your first project assignment, where you have to look at correlation between income, or at least financial status, and crime rates, that's already 2 variables. So really, when we want to use statistics and we want to use it to compare things, we can't just use one variable, right? We're going to have to use more than one variable, and that's what I want to talk about for the rest of this class. I want to talk about what happens, right, when you have more than one random variable. I'm going to prelude this discussion with a bit of a caveat. I like in this class that we get to know each other. I get to know your study habits, maybe how you think a little bit when I read your project. And usually through office hours or whenever we talk after the class, I get to know you a little bit better. And throughout my 3 hours of rambling, I get to know a little bit of me, right? Now, I know that I've been nothing but a joy and a light in the darkness that is this summer semester, but there's always
confidence.
What?
I like confidence.
Thank you. But I mean, there's always negatives to everyone, right? I mean, you're not perfect. So neither am I.
Okay, great.
So I will tell you one negative thing about me, and one thing that really pisses me off. I like it, when we can work together and solve things, and you've taken another class with me, so you kind of know that that's kind of my style of teaching. But I also, I also believe in personal responsibility. I'm a conservative, so I believe in personal responsibility. And believing in personal responsibility means that I do want you to put in your effort for your grade. The other day, your grade is your grade, that doesn't really affect me. Nobody says they need to meet a quota of grades to keep your job now. I have failed not entire class, but I feel like majority of classes before, back when I was here, so I don't mind. So whenever we talk about joint probability distributions, and this has been every single time I've taught this class, whenever I talk about joint probability distributions, I prefer to solve examples using Excel, because it's a lot of stuff. It's a lot of calculations that are repeated. Instead of repeating them over and over again manually, I just write them in Excel. I share my computer screen with you. You can see what I'm doing. And my expectation is for you to follow along, which is why I asked you to bring a laptop. If you don't want to follow along, that's also fine. It's not a big deal. I will recommend that you follow along this time, because there will be an in-class problem. It'll be just faster if you do it on the computer. That's it. You can work in pairs, by the way, if you don't have a laptop. But then, if you want to follow along, good. If you don't, that's also. What really pisses me off is that throughout class, we typically spend a long time, because I want you to write down everything. I want you to write down everything. And I want to make sure that we can all be at the same pace. I don't want to have you be 3 steps behind, right? I do it for you. But then there's always one student, I don't know why, there's always one student that sits back and says, I'm not going to do anything, and just waits. And okay, that's your decision, I don't mind. But then at the end of the class, what do you think they ask me for?
Can you explain?
Copy of the
can you upload your Excel into D2L? Right after I'm going like slow, waiting 5, 10, 15 minutes at a time for everyone to catch up, and can you just upload that to D2L so I can use it? And I get really pissed off, and that's when like the joy and sunshine that I am suddenly turns into like this ogre that you're like, oh my god, why did I register for this person's class? I want this semester to be the exception, and I want this semester to be the day where I am joy and sunshine for the entire semester.
Also, you will post it.
No!
-1.
I brought my laptop, okay?
Jesus, Ramtin.
Why not?
I just wanted to show the entire class that you still can be not the sunshine too often.
Yeah. Jesus. All right, give me a second to just breathe in and see. If this was 3 years ago, I would have responded much differently than I'm responding now.
But if it was 3 years ago, I wouldn't even ask it since you told me, you know?
Yeah, that's true.
This throws me.
No, now I gotta show my maturity of being almost 30 or something. So, breathe in, breathe out. I'm gonna find a way to screw you over something. I don't know what. Maybe a test. It's gonna be a grade, maybe an extra credit that you missed for some. I'm gonna find something.
Okay, so you already have a reason I wanted to talk about you, but I'm not gonna say anything now.
Yep. All right. Yeah, all in fun. Yeah, just try to follow along with your computers. Just follow this in Excel, right? And I will not post it on D2L, right? You'll have your computers on it. Okay. Let's talk about joint probability distributions. Let me just write it down. Joint probability distributions. Whenever we have more than one random variable, we have an option. We have two options. You can either study one variable and then study the other variable, or you can study both variables at the same time. The latter is typically the preferred method because sometimes one variable is going to affect the other variable. Right? So the concept of a joint probability distribution is a probability distribution that consists of not one, but two or more random variables. In other words, if we want to study two variables at the same time, we don't just look at the probability of one variable being equal to one thing. Instead, we look at the probability of each of the variables being equal to some value. That's what we call a joint probability distribution. For discrete random variables, so I used to use x a lot, now let's use x and y. So for x and y being discrete random variables, then my joint probability mass function can be written as f of x and y. And of course, it needs to be evaluated at some value little x and some value little y. What do we know about this? Well, for starters, it needs to be greater than or equal to 0, right? And obviously it cannot be more than 1 either. So there's no such thing as negative probability. We know that if we were to add up all of my values in my joint probability distribution, through all my possible y values and my possible x values, that should give me 1, just like with a one variable distribution. And finally, the actual definition is that my joint probability mass function, f of x and y, all it does is it just gives me the probability that one of my variables, x, is equal to the first variable, little x, and my other variable, y, is equal to little y. That's my joint probability distribution. For continuous random variables, just like with variable distributions, we don't just have probability functions, instead we have probability density functions, but they still follow the same properties, right? First of all, we know that it has to be a number greater than or equal to 0. Instead of adding, we would integrate. So if we integrate the joint probability density function throughout the entire sample space, that should be equal to 1. This is x, this is y. I guess capital X, capital Y. That's a little bit better. And in two-dimensional space, because now it's it's two variables, so we would be dealing with two-dimensional space. Then we can say that the probability that my two variables x and y are within that two-dimensional space, let's just call that space R, and that should be equal to the integral of my probability density function. Like I mentioned, we're not going to be doing too much with continuous variables. I prefer to deal with discrete, although continuous are definitely more fun from a math perspective, but I do want you to focus on statistics. So, but yeah, those are the properties of joint probability distributions. One example of a joint probability distribution is in your book. Oh, I didn't write down the page. So one example is in your book, and I didn't bring my book. If you go to section 5.1, the very first table in that section will give you a joint probability distribution. It's a nice little table. We're actually going to use it, and we're going to type it down in just a second, but just to give you a heads up, that's one of the examples of a joint probability distribution. I guess I'll just write it down because I didn't bring my book. Does anybody have their book with you? Okay, fine. I'll just write it down. I'm not that lazy. This is an example of response time and signal strength. And the idea is, we're measuring signal strength and signal response time. Those are two different variables, and then we put together a table with a probability distribution for these two variables. Of course, they both may be related to each other. So what I'm going to do, and this is just we can call it an illustration, not really an example. What I'm going to do is I'm going to let X represent my signal strength. I'm going to let Y represent my response time. An example of what a joint probability distribution would look like would be to plot my signal strength and my response time in two different axes, and then just create a table with different probabilities at each different point. I could, for example, define my signal strength as 1, 2, and 3. This is just my X values. And my response time as 4, 3, 2, 1. Those are that's my sample space. Now, what the joint probability distribution tells me is what is the probability when x equals 1 and y equals 4? And that's a value here. It's 0.15 in your book. But then we also have the probability when x equals 1 and y equals 3. And so on and so forth. Now, you'll notice that for our joint probability distribution table, we can't just say, well, what's the probability that x equals 1? Because we need both x and y values in order to assign a probability to it. You may think that I'm just teaching this class, but in the back of my head, I'm still planning on revenge. So I'm a bit of a multitasker there. All right. This is what we call a joint probability distribution. All it says is, well, what's the probability that x equals 2 and y equals 3? Well, in this case, you look at x equals 2, you look at y equals 3, that probability is 0.1. So it's a two-dimensional table instead of a one-dimensional table that we've already been used to using. The different properties of a joint probability distribution, some of those will be helpful for us. I would say the most helpful property would be to determine what's called the marginal probability. So my joint probability tells me the probability that x equals x and y equals some value y. So we need always to define the two variables. My marginal probability tells me, right, what is the probability of one individual variable occurring regardless of what the value of the other variable is. For example, I can look at this table and I can say, well, I don't care what y is. Y can be 4, 3, 2, 1, it can be whatever it wants to be. I just want to know, regardless of what y is, what is the probability that x equals 1? Just looking at this table, do you think there's any way we can figure that out somehow? When I say what is the probability that x equals 1 regardless of y, what I'm saying is what's the probability that x equals 1 whether y is 4 or 3 or 2 or 1. So is there any way to extract that probability from that table?
Add up the ones.
Can you say that a little bit louder?
You just add up the ones.
That's correct, right? If we say we want the probability of x regardless of the value of y, then that means we need to include the probabilities for all the values of y, because any one that could occur. Are you Bailey?
Yep.
Okay, so what Bailey says is to add up all the values in this column. In this case, we have 0.15, 0.02, 0.02, 0.1, 0.2. I think that's 0.2. And what this is telling me is that the marginal probability, I'm going to write it down as f of only x, right? So it doesn't matter what y is. So the marginal probability that my x variable is equal to 1 is going to be 0.2. Now I could easily ask you to find the marginal probability of x equals 2, 3, or x equals 2, x equals 3. I can ask you to find the marginal probability of y equals 1, 2, 3, 4. If you combine all those values into two little nice neat tables, one for x, one for y, we call that a marginal probability distribution. So, of course, there's a lot of adding to do. So I think it's better we just work through it. Let's work through the entire table so that we have, some practice with this. See if this computer has Excel in it. It should have. Online students, I'm working on the computer right now, so you can't see anything, but I'll share it with you as soon as I get a chance. All right, online students, are you able to see my computer? No, wait, yes? Okay. Okay, that's good. It's kind of small, let me just zoom in a little bit. So I'm going to write down this table so you have it, and because I'm also writing it down, we can all write down at the same time. So I'm going to have my x values. I'll just call this, I'm using my computer, my laptop keyboard. That's dumb. I'm going to write down my x values. Let's see. 1, 2, 3, where my signal strength. I'm going to write down my y values, 4, 3, 2, 1. I know that this corresponds to x. And I'm not going to use the term signal strength response time because I really just want this to be as generalized as possible, and this corresponds to y. To make this a little bit nicer, let me just merge this here. Make it look better. I'm going to add borders here. And maybe a thick outside border. Yeah, that looks nice. Let me even change the background. Notice how I'm stalling for time to make sure that everybody has it. What color do you want? Oh, let's just use gray. Awesome. I'm going to write down probabilities. Those were 0.15, 0.02, 0.02, 0.01, 0.1, 0.1, 0.03, 0.02, 0.05, 0.05, 0.2, 0.25. Go and just do this. Nice. All right. So I have my little table. Maybe I can make it even bigger so that online students can see very well. And I would like to know what the marginal probability distribution of x is. So this is my x. I would like to know what the marginal probability distribution of x is. Now in the example, we found the probability of x equals 1. And we found that by adding up all the values in this column, right? I guess you can just let me know when you have it ready. Jay in the chat says that I am an Excel wizard. That's a nice little compliment I've never gotten before. Not sure if I should be proud or not proud of that.
How did you put that y in the middle?
I mean, this is the vertical alignment, this is the horizontal alignment. All right, online students, we're just waiting on some of the in-person students to wrap up, and we'll start in a second. And we have time today, so don't worry, we're not going to fall behind or anything. Are you done?
Yeah, I'm done.
Oh, we're
Doing
waiting for you.
something else.
All right, so this is our joint probability distribution for two variables x and y. We already said that if we want the marginal probability, so the probability that x equals 1, regardless of the values of y, all we have to do is add up all of the values in this table. And we got a probability of 20% or just 0.2. It should follow that if we want the marginal probability of 2, we should add the values in this column. Is that correct? We want the probability that x equals 2 regardless of y. And then if we want the probability that x equals 3, okay, so let me just expand this a little bit. And what this is giving me is the marginal probability, so f of x, of the variable x. Yep. I'm going to write this down in a different color, just so that we don't get it confused with the joint probability distribution. What this is giving me is the marginal probability of x. You can write it down in a nicer table, maybe a table that relates x to the marginal probability of x. So for 1 it's 0.2, for 2 it's 0.25, for 3 it's 0.55, but for me this is actually okay. Michael, describe the process. I mean, not Excel, but like the mathematical process of finding the marginal probability for y.
It would be adding up the rows.
Okay,
so for marginal probability of 4, it'd be 0.15, 0.1, 0.05.
Okay, that's good. So Michael says that if we want the marginal probability of y, all we have to do is add up all the rows. Get rid of this. It's annoying for me. So this is f of y. Can I give it a slightly different color? Again, so that we don't confuse it. All right. Let me know when you have this ready, so we can move on. Okay, so now that we have this, essentially what we have here is a joint probability distribution and then two marginal probability distributions. Can you identify what the joint probability distribution is here? Maybe let's work our way backwards. Can you identify the two marginal probability distributions?
Not the F column and 7.
Right. So here's one, right? Here's the other one. And then what is a joint probability distribution then?
One. What's in the middle?
The ones in the middle, right? This is my joint probability distribution. It's good for you to keep in mind the difference. Normally, I would normally ask for you to write 3 different tables, one with the joint, one and 2 with the marginals. But I think this is fine as long as they're identified. So as long as you tell me that this is the marginal probability distribution for this variable, and this is the marginal probability distribution for this variable, so x and y, then that should be good enough for me. Let's see if we understand a little bit of what a joint probability distribution is like. First off, if you were to add all these numbers in only the marginal probability distribution of x, what would that equal to? Only x. 1? Okay, good. I believe you. Let's just write it down so that we can all see it for ourselves. 1. So notice that just like any standard probability distribution, the marginal probability distribution also has to add up to 1, because it does include the entire sample space. You may think, wait a minute, but it doesn't consider y. But it's okay, because it actually considers all the y's. So if it considers all the y's, then it's already taking into account the entire sample space. Likewise, the marginal probability distribution of y should add up to 1. You can see it here, 1. What if we add up all the values in my joint probability distribution? What would that be equal to?
That's still equal 1, right?
Still 1, right? Because it is still the probability distribution. In fact, all we're doing here is we're just adding the same numbers in slightly separate ways, in a different order. So it's always going to be 1. One good way to check that your distribution is correct is to make sure that your joint probability distribution adds up to 1. And then your two marginal probability distributions add up to 1 as well. Any questions? Simple enough, right? Good. That's good. I think the analysis of 2 variables is definitely it's a good step into using statistics to correlate things. Okay, and we're definitely going to talk a little bit about that in a second. All right, so we talked about the marginal probability distribution for a discrete random variable, which is just adding up all the cells in the corresponding column or row. What if it was continuous? We wouldn't really be able to add up, right? What would we have to do instead? Integrate, correct. It's the same process, except that instead of adding up, we just integrate. We find areas, right, on the curves. For marginal probability distributions, right, we still need to find measures to study them. I would say the first measure, the one that we always look into first, is the mean. And here, we want to be careful because we don't really calculate a mean for the joint distribution, right? We can't really calculate a mean for the two variables combined. Because you see from the table that we just did in Excel that even the different variables, they had different lengths. One was 3 values, one had 4 values. So we can't really calculate a mean for two of them combined. Instead, we are going to have to calculate the mean for each individual variable. Time to go? All right. Little parenthesis here. Have you ever forced yourself to speak a certain way in that, to the point where it just feels normal to you and everything else doesn't? So I've done it several times. It's kind of weird. I say compute it a lot. So I would say compute it for each individual value. And compute and calculate, they're both correct. I would prefer to say compute it just because calculate it sound like, to me, it would sound like I would just transliterate from Spanish. Not even translating, like transliterating from Spanish. And it just felt weird. But to compute is when you calculate things with an algorithm, right? And when you calculate, just calculation. So a mean, for example, you can say that you compute the mean because you follow some steps in an algorithm, but you can also say that you calculate it because it's all just numbers. There's no if-else statements. So I used to say compute a lot. I would never say calculate. It sounded weird to me. But then I started training myself to say calculate because I was using compute in the wrong contexts. So now I just say calculate it to the point where saying compute just feels wrong to me. And it just comes out naturally. It's happened a lot of times. When I was a teenager, I was dumb, so I would write anyways with an S at the end, and I thought that was normal, but then I realized it wasn't, so I forced myself to say anyway, and now I hear someone say anyways, and I'm like, what is dumbass? Doesn't happen. So it's kind of weird how you can rewire your brain to do certain things. It's a little bit scary. Just so that you know, if you have some habits that you feel that, oh, I'm not going to break this habit, it is possible to break them. It's just a matter of training yourself and just like forcing yourself to do something. But anyway, parentheses over. The mean is calculated for each individual variable. In other words, we'd have to calculate it using the marginal probability distribution. Normally, what I would write is mean of x, mean of y. Or, if you prefer, you can perhaps write it as the expected value of x, the expected value of y. We're going to use a bit of both in this class, both notations. But whenever you are showing me means for what's essentially a joint probability distribution, remember you have to explain if you are using the mean of x or the mean of y. So always mark that down. X, y, there is no mean for the whole distribution. There's no one value. There's a mean, right? There's for x and y, but there's no one value that gives you the mean for the whole. Variance and deviation are also calculated in the same way. When I say in the same way, I mean that we calculated for our individual variables following the marginal probability distribution. You want to specify if it's x, if it's y. You may want to also just use the function, variance function. Or if it's a standard deviation, once again, you specify if it's x or y, or you just use the function. Whatever's easiest for you. Like I said, I'm going to use both just to get used to both styles. Now, just because these measures are calculated for individual variables doesn't mean that there isn't a way to relate the two or to calculate measures for the probability distribution as a whole. There are ways, and we're going to look at those. But just to keep in mind, we can calculate mean, variance, and standard deviation for individual variables, and it's the same procedure, right? The same procedure that we've already done. If we go back to that table we looked at, and I don't have to show the Excel again, I think I can just show it here. If we go back to this table, we have different probabilities for different values of x and y. Now, there's something interesting here. Notice that, for example, if I want x equals 1, my probability actually depends on what my value of y is. Right? If y equals 4, then I actually have a higher chance of landing x equals 1, right? But if y would equal 2, I would actually have a smaller chance, much smaller chance of landing x equals 1. When one, and let me just use terminology from the previous weeks, when one event, right, affects the other event, there was a name we had for that type of probability. Does anybody remember? Let me see if I can give you the answer without giving you the answer. When the likelihood of something happened was conditioned on something else occurring first, there was a name for that type of probability. Conditional probability, correct? Yep. So conditional probability, just so that we can remember, conditional probability was the probability of one event occurring given that another event has already occurred.
So what in general, regardless of y, the probability that we get 1 is 20%, right?
I mean, regardless of the y.
Yeah, regardless
yeah.
of
But then we can also think after we find the y. Let's say y comes first.
Okay.
After we find the y, then what is the probability? It's not really going to be 20%, it's going to be something else, right? So it's pretty interesting to see how this works, right? And thank you in the chat for showing the notation, right? P of x given y. In this case, the probability that y equals 3 and x equals 1 is 2%, right? We can see it from the table. However, let's say that y already equals 3. That's already done. It's already been measured, so we don't have to guess it. It's already, we know that for a fact that y has already equaled 3. If that is the case, then what's the probability that x equals 1? So we already know y. It's no longer a random variable. It's already an outcome. We already know what it is. So in that case, what is the probability, okay, that x equals 1?
It'd be 0.02 over 0.17, right?
So it says 0.2 over 0.17. Where did you get the 0.17?
Added up all the three values.
You added up all the three values? What three values?
For where y equals 3.
Okay, so you added 0.02, 0.1, 0.05? Yeah, okay. Can you explain the reasoning behind that? You are right.
So if it can only equal y, then that changes the probability of the whole thing. So now you would just take, if it's the probability of 1 of the 3, you would take that probability over the total and give you a new probability.
So if I understand correctly, what you're saying is, if y equals 3, that means that all of these are gone, right? They're no longer part of my experiment, right? Which means that all that's left are these three values of x, 1, 2, 3. But because that's all that's left, what does that have to add up to?
1.
Still have to add up to 1. So that means that we need to take these in terms of a proportion, right? As a whole. And what you do to find the proportion is just to divide it by the total sum, right? Good. You may recall the idea behind conditional probability. I think we mentioned, if I remember correctly, that the probability of some event B given A is equal to the intersection of B and A, or A and B. It's the same thing. Divided by the probability of A. Was that the equation? I think that was the equation. So I would like to find a way, and this is taking what Bailey said. I would like to take everything that Bailey said and just put it in here. So express this or generalize this in a way that can help us find our conditional probabilities for joint distributions. In this case, the probability of B given A can be taken as the probability of one variable given that another variable has already occurred. In other words, we can look at this conditional probability as the probability, and let's just say, look, we're going to say that y equals some value, given that x already equals another value. And we find that probability by looking at the intersection of A and B. In this case, what is the intersection of A and B, or x and y? Well, it's the joint probability, right? It's a probability that two values have already occurred. That's the intersection, that's just my joint probability. But then we divide it by the probability of the first event occurring. Now the first event is just x equals x. So that probability cannot be a joint probability. It has to be a marginal probability. So we can find our conditional probability between two variables by taking the joint probability distribution, by taking the joint probability and dividing it by the marginal probability of that first value. The notation for this is typically f of y given x for a specific value of y. And then we say that that's equal to the joint probability distribution divided by the marginal probability. You can exchange x and y here. But that's essentially how we find conditional probability. We can also find conditional probabilities for continuous random variables. You can read that in section 5.2. That's outside of the scope of this class. You can look at section 5.2 if you're interested. If we go back to the table, we said that we wanted to know what is the probability that x equaled 1 given that y equaled 3. So what we have to do is, well, we're essentially being asked to find the margin or the conditional probability of my variable x given a variable y, where my variable x is equal to 1. In this case, my variable y is equal to 3. Following the equation, this is found by taking the joint probability distribution of both values. So the function fxy of x equals 1 and y equals 3. And then divided by the marginal probability of the first event. My first event is y equals 3, so this would be the marginal probability f of y of 3. I think you've already answered this before. I'm just going to ask again, what's the probability that x equals 1 and y equals 3? 0.02, correct. It's right here. And then what's the marginal probability that y equals 3?
0.17.
Yep, the sum of all these, which is 0.17. Okay.
It's sum of all what?
Can you say that again?
The over. That's for y is 3. I thought you meant you had those numbers.
Yep. But it's a little bit easier to you. You can look at your Excel spreadsheet and look at the marginal probability of y and then just find rather 3. We'll find 0.17. So 0.02 divided by 0.17 is what?
1.76.
117?
118.
Okay. So notice that the probability that y equals 3, x equals 1 is 2%. But if y is already 3, if we already know that, then my probability increases to 0.11, to 11%, almost 12%. Now this is actually something interesting, because it does lead back to Bayes' theorem and Bayesian statistics, right? Remember, we said that the idea behind Bayesian statistics was to update our knowledge with new data. And that's exactly what we're doing here. We had an initial data, an initial probability, which was initially we thought the probability that, and let's say we're just looking at x. Initially we thought the probability that x would equal 1 and y equals 3 is just 2%. However, now that we know, right? Now that we know in the future, the events occurred. Now that we know that y equals 3, that probability increases to 12%. You could express it differently. You can say, well, initially, let's say I don't care about y. I only care about x. Initially, the probability of me landing x equals 1 is 20%, right? Regardless of the y. But now that I know that a y occurred, my probability actually decreases to 12%. It's actually a fun example, also probably related with cars, right? Where you had some probability, given whatever cars you choose, and then choosing a card is different. I'm going to look at the example and maybe share it with you in the next class. Because even though this seems very intuitive, just thinking about it, yeah, new evidence should definitely alter your perception of things. It does end up being a little bit counterintuitive sometimes when you look at it, when you start applying it to things like drawing cards and stuff like that. One interesting thing about Bayesian statistics, which I didn't really cover in detail in the last class, but maybe future classes where I teach it, I'm going to try to go into more detail. One interesting thing is that according to Bayesian statistics, probability is not really objective. Right? There aren't numbers. There are just measures of how confident we feel for something. And a lot of statisticians disagree with Bayesian statistics because they say, well, no, we can't just go all subjective into it. There needs to be numbers, there needs to be organized things. But really what Bayes would say, or his followers would say, is that there are no numbers, right? There is no numerical probability, really. There's just how much you feel that something can happen given the information that you know. And the information that you know may be different to the information that you know. Therefore, both of you could have different probabilities in mind for the same event because you have different information about said event. So you can quantify it, you can add numbers to it, but you can still end up with different results, right? And that's all based on the current evidence that you already have. So that is the conditional probability for a joint distribution. So there are three things you want to find, right? Joint probability that requires two values, marginal probability that's only one value regardless of the others, and conditional probability that's one value given that another value has already occurred. So those are the three that you want to consider: joint, marginal, and conditional. Yeah?
So you can't really say that bringing down the number of variables brings up the probability.
Not always. That's the thing. It could be higher, it could be lower. Because in the case of the example we did, it really depends on how x equals 1 fits into y equals 3. When that proportion could be different. And that's something that you really want to keep in mind. Not you, the general you, everyone. You really want to keep in mind because there's interesting examples where actually knowing something doesn't necessarily mean that you will increase your chances of getting what you want. So has anybody ever played solitaire cards? The Klondike game where it's just like, okay. So I like to play that game. I'm actually pretty good at it. I think I'm pretty good at it. And one of the things I used to think back when I was just not normal at it was I thought, well, the more cards I see under the deck, so then the better chance I have of solving this because I know more stuff. But that was actually not really the case. Because in some instances, actually knowing a little bit more would decrease my probabilities of actually making a correct move or making a correct guess. That doesn't just happen with solitaire, it happens with Sudoku. Has anybody played Sudoku? Mm-hmm. Okay, same thing. So with Sudoku, one interesting thing, I can explain it from a theory point of view, I just can't explain it intuitively. It still really bogs my mind is that I can pretty much solve any Sudoku you throw at me. However, sometimes if I go too fast at identifying correct squares, even though that means that I should probably be able to solve it even faster, knowing more squares, I get more lost. It becomes harder.
Because after each, you have to look for the other one that's related. So if you find a new 7, you have to look for other 7s. But if you're doing it too fast, like you find another one, it's harder to find.
And not just that, it's also the fact that some of the strategies require you to not know something in order for you to actually be able to complete them. And that's one of the beautiful things about it, right? There are some strategies like having I don't really know the names of the strategies because I'm not like I don't know the names of the strategies, but there are some strategies where if you have combination of two numbers, all in the same square, and then the same two numbers in a different square but on the same line, then the one above it cannot be either of those two numbers. That only works if you don't know those three squares. If you already want those three squares, there's no way you can apply that rule, and then you could never figure out that. And that's why I think it's a very interesting thing, right? It's like you may think that the more you know, the better chance you have of something. It actually doesn't always work that way. And it's pretty interesting. Sometimes when you are doing some gambling as a card game, it's actually better to not know some things. Okay, we'll get to a point where we gamble for a grade, but not yet, not now. All right. In addition to my conditional probability, we can also find conditional means and conditional variances. We say the conditional mean, and I'm just going to use the function. We can express it as the mean of y given x. And I'm actually going to write down just the general form of it, the integrated form, I guess. And that's just the integral of y times my conditional probability of y integrated across my y space. That's it. We're not really going to use this. This is actually more applicable to continuous probability distribution, so we're not going to use it in class, but I think it's still important to have somewhere there the conditional variance. It's going to be the integral of y minus the conditional mean squared times my conditional probability distribution. It's actually the same equation, except that instead of using marginal probabilities, now you are using conditional probabilities. That's all it is. So the equation is still the same mean equation, except that instead of using marginal probabilities, you're using conditional probabilities. We may not actually need to talk about this. If we do end up bringing it up in the future, I'm going to do a reintroduction to these terms and maybe cover it in a little bit more detail. For now, just keep in mind that you can have conditional means, conditional variances, and of course conditional standard deviations, which are just the square roots of the variance. I realize that I've actually went a little bit ahead of time. I usually want to take a break after an hour 15. So let's take a break. It's 3:21. Let's meet back at 3:35.